Yeah, okay, so thank you for coming to my seminar. So the work I'll be presenting is about a new multi-party computation protocol that addresses two of the major constraints that we can find commonly in deployed systems. I will also be presenting this in exactly 2 weeks at AsiaCrypt, and this is joint work with Emad, Emanuela, Nigel, and Oliver. Okay, so the goal of MPC is to allow a group of parties to compute a joint function over their inputs without having to reveal these inputs to each other. And even if there is some adversary that controls a percentage of the parties, this adversary should not learn anything other than the final output. Now, when designing MPC protocols, there are a few common assumptions that we make it easier to design efficient protocols, but that also make the protocols a bit more unrealistic for many scenarios. So the first of these assumptions is that we assume that between each pair of parties there is a dedicated fast communication channel. And if we have a lot of parties, or if there's a party who is running multiple MPC computations with different sets of parties, then building these communication channels might not be feasible. Then the other assumption is that parties should stay online during the full computation. So usually what happens is that if a party drops out for lack of resources or some other reason, the protocol aborts and all the work that was done up to this point is lost. So in this work, we want to look at these 2 points and build something that is more in line with what exists today in the real world. Okay, so let's see an overview of what we did. So first, instead of having this type of communication topology, we have a star-like communication topology with a few relay nodes. So we don't have to have only 2 relays, we can have more relays, but we need at least 2, and I will explain why later. So instead of having to establish one communication channel for each other party, I just need to ensure that I have communication channels to these few relay nodes. And these relays, they act as storage. So when I send a message, the relay will keep the message stored until the party that the message is for decides that they want to receive the message. And this is actually helpful for the next point, which is that we allow parties that are slow or that have delays. So we are still in a synchronous network, meaning that the protocol proceeds in rounds, but we allow parties to have a delay of up to a certain number of rounds. So this delay can be because the party just is slow doing some computations or has bad connection, or the parties can even drop out completely. And then when the party is available again to recover the messages that were sent in the meantime, the party can just ask the relays to give them the messages that are there for them. And also we allow a group of faster parties to progress ahead in the computation. So even if some parties are delayed, the faster parties can move ahead and don't have to wait. Now, there are a few previous works that have a few of these characteristics, but not all of them. The work that's more similar to ours is this White City paper, where they also have relay nodes. But here, the relays have to constantly run a consensus protocol to ensure consistency between them. And in our work, we show that this is not necessary. And there are a few other differences. For example, they don't have any type of consideration for the size of the state that the relays have to store. Then another work is a paper by Ben Hamouda et al., where they don't have relays, but they consider delays. So here the parties can be delayed, and also the faster parties can progress ahead in the computation. But the way their delays work is a bit different. They have an upper bound of on the number of messages that can be delayed per round. Also, their multiplication protocol has some extra overhead compared to ours. And these are some of the differences. And then there's also a few works on multi-party computation with dynamic participation. One of them is this Phoenix work, where parties can drop out and come back again. But here, the parties that drop out, they are never assumed to recover the messages that were sent in the meantime. And the way they ensure that the protocol can keep going is by having a lower bound on the number of parties that stays online from one round to the other. And again, they do not consider relays. So now I will show you how we build our protocol, how we put together these relays and the delays in the same protocol. And the first building block is Shamir secret sharing. So with Shamir secret sharing, if I want to share a secret, I just need to sample a random polynomial such that the evaluation of p at 0 is my secret. And the degree of this polynomial will tell us the number of allowed corruptions. So if the degree of the polynomial is t, we can have at most t corruptions. But for Shamir secret sharing, we also know that we need to have a honest majority. So the total number of parties, n, should be at least 2t plus 1. And if we want to allow a maximum number of corruptions, we can have that n is exactly 2t plus 1. But in this case, we are particularly interested in the strong honest majority setting, where n is strictly greater than 2t plus 1. And the reason why we are interested in this setting is because here we have some redundancy, and this is what will allow the faster parties to progress ahead in the computation. So even if some parties have delays or are slow, if we have at least 2t plus 1 parties that are ready to move on to the next step, then we just need 2t plus 1 parties to carry on the computation. And of course, the larger the difference is between n and 2t plus 1, then the more likely we are to have a faster group of parties that can move on and arrive quickly to the end of the protocol. Okay, so this is the secret sharing. Then the next building block is the relays. And the relays allow us to do send two types of messages. We can have both point-to-point messages and broadcast messages. So first, let's look at the point-to-point messages. So let's say there's a party I who wants to send a message to party J. And here I will assume there's a previously exchanged set of pairwise keys. But in the paper, we explain how to do key exchange. So party I wants to send a message M to party J for a certain round K. Then party I just needs to encrypt this message using these pre-exchanged keys and send the ciphertext to the relays. So both relays will store the same ciphertext. And then whenever party J is ready, they can just ask the relays, please send me these messages from party I for this specific round. Then party J receives the ciphertext and can decrypt them. Now, this party will only accept the messages if they both decrypt correctly and if they decrypt to the same message, because this is how the parties will detect malicious behavior from the relays. So this is why we want more than one relay, because we allow relays to be corrupted. And if at least one relay is acting correctly, then if some other relay sends a wrong message, then this will be detected by the parties. Okay. So these are the point-to-point messages. So we have these commands, the send, request that I already mentioned, and also an erase command so that parties can tell the relays, please erase these messages, I don't need them anymore, so the relays don't run out of storage. And the relay will maintain pairwise counters for both the received messages and the messages that were already deleted. Then for the broadcast messages, they are actually very similar. So, of course, there's a difference that every party will receive a broadcast message, which means that parties don't need to encrypt the messages when they send them to the relays. But other than that, it is very similar. So there are dedicated commands for broadcast and also these global counters that count the number of received broadcast messages, the number of deleted broadcast messages, but other than that is exactly the same. So while in usual networks we have that broadcast is more expensive than point-to-point communication, here broadcast is even cheaper because we don't need to encrypt the messages before sending them. So this will be very useful when building our multiplication protocol later. as we will see. Okay, so before we build the protocol itself, we need to know what kind of security do we want to achieve. So we are using Shamir secret sharing, and as usual, the adversary can corrupt MPC parties, and because of Shamir secret sharing, this can be up to a minority of the parties. Then, as I also already mentioned, the adversary can corrupt relays as long as one of these relays remains honest. And then the adversary can delay an arbitrary number of parties as long as this delay has an upper bound of delta rounds. Okay, so what we build is a protocol that is passively secure against this adversary, but actually we would like to achieve active security, so we don't want just passive security. And for that we use this result from previous work that tells us that if a protocol is passively secure up to additive attacks, which means that if the only thing that a malicious party can do is add additive errors, then we can compile this protocol and obtain an actively secure protocol. So we can find a way to detect this type of additive errors. And the way this is done is by essentially running the same circuit twice. One of the times we run it on the actual inputs, and then we run it in parallel on this randomized version of the inputs. And so when we run these two circuits in parallel, and then at the end there will be this checking equation that will tell us if there was some additive error added or not. And the way we calculate this checking equation is quite similar to what is done in the fluid MPC work. So instead of computing the full equation at the end of the protocol, we compute it step by step, because this will prevent us from having to store very large states. Okay, so our goal now is to build an MPC protocol that is passively secure up to additive attacks. Now, because we have linear secret sharing, we know that linear computations are completely local. So these additive errors can be introduced during multiplications. So we have to look into how are we doing the multiplication with MPC. So first we try to look at Maurer multiplication. So here the parties start by locally multiplying their shares, and then they obtain a secret sharing of the result, but it's a secret sharing using a polynomial of degree 2t. So then they want to convert it back to a degree t polynomial, and for that they secret share the values they obtained in step 1. However, there's a problem in this step, which is when the parties do this resharing, they can actually introduce different additive errors for different sets of parties. So this means that this error is not uniquely determined for all the parties. And so this means that we cannot use this multiplication protocol. Okay, then we can look at the standard Damgard-Nielsen protocol. So this is a 2-round protocol, so we have one more communication round. We also require some pre-generated randomness for this protocol. And the way this proceeds is that, again, the parties arrive at some sharing of degree 2t, and then there's this central party called the king that will receive the shares from all the parties and reconstruct the value and reshare it. However, there is a known attack for this protocol in the strong honest majority setting. So if we have a strong honest majority, this party, who's the king, can actually mount an attack in order to recover the secret shares of other parties. So this means that we cannot use it again. But what we can do is to use a 1-round version of the Damgard-Nielsen protocol. So in this 1-round version, instead of having a king who receives shares from every party, what happens is that every party will open their shares to all the other parties. So it's as if all the parties act as the king. And usually this would result in a more expensive communication because we are using broadcast. But in our protocol, broadcast is very cheap, so actually this is much better than the previous 2-round protocol, because not only we have a single round, we also have a less communication complexity. And also this is secure up to additive attacks, so we can use this protocol in order to build our maliciously secure MPC protocol. Okay, then we also implemented this protocol and tested how what overhead is introduced by this new network. So first we wanted to analyze the effect of introducing relays in the communication. And for that we did multiple experiments. So we compared direct communication, so without relays, with communication with relays. And for the relays, we tried different types of experiments. So we have an experiment where messages are never erased. We have another experiment where after every message is received, the party requests that this is also erased. And then we also have erasure in batches. And then we also have a last experiment with where the messages are much larger than in the previous ones, just to see how this affects the speed of the communication. And what we can observe is that, so this is a logarithmic scale, and what we can see is that up to a certain point, they all have very similar running time, but at a certain point, the experiments where we never erase messages or where we erase every message after it arrives, they become much more expensive. This is because we are either constantly requesting the relay to erase messages, or if we never erase, then it means that the relay will take more time to find our message in the storage. So the ideal thing that we should do if we want to have similar running time to direct communication is to just erase messages in batches. Okay, then we also did some similar experiments, but for broadcast messages. And actually what we see is that here there's no problem with not erasing messages or erasing messages one by one. And this is both because this experiment is a bit different, because here in broadcast messages we have that every party is both a sender and a receiver, and also because the way these messages are stored is different from the point-to-point messages. So possibly we could maybe improve the way we store point-to-point messages so that the case where we never erase any message is also a bit faster. But the truth is that we always need to erase messages, or otherwise at some point we will run into a storage limit. So still, I would say that erasing messages in batches is the best approach. Okay, so finally, we also took a look at the MPC protocol itself. So we tested the running time for multiplications. So the way we did this is that we tried batching an increasing size of multiplications per round, and then we measured the number of multiplications per second that we achieve. And we did this for both a situation with 3 parties and 6 parties. And the interesting thing is that for 6 parties, we chose 3 parties that are run on faster machines. And this sort of simulates a situation where there are delays. And indeed, what we can see is that the faster parties in this 6-party case, they have around the same amount of multiplications per second as the 3 parties. So in the 3-party case. While this line with the lower number of multiplications, these are the slow parties from the 6-party protocol. So in the end, what we obtain is that if we have the maximum batch size, we can actually get a 270,000 multiplications per second for the faster parties. And this is for a not particularly optimized version of the implementation, so we predict that we could maybe achieve 1 million multiplications per second for more optimized implementation. Okay, just to wrap up, so we introduced this new MPC protocol where we have a different communication topology, and we show that it is secure even in the presence of delays. We also discuss how to do multiplication in this setting, and finally we show some experimental results. Now in the paper we have a few more things. For example, we talk about key agreement, we also discuss the size of the state that the relays have to store in different situations, and also we have some ideas for optimizing the communication and around complexity. Yeah, so that is it from me. So if you have any questions, go ahead.